Zirconia. It's one of those amazing materials you find everywhere, from super strong dental crowns and hip implants all the way to jet engines. We think of it as this powerhouse, right? Almost unbreakable. But what if I told you that deep down, at the atomic level, there's a secret war going on? A conflict that can flip this superhero material into its own worst enemy. So, let's pull back the curtain and uncover the hidden life of zirconia.
So here's our game plan. We're going to start with zirconia's kind of chameleon-like nature. Then we'll meet the two main players in this internal drama, the tough guardian and the steady giant. You'll see how they team up to become a really problematic duo. And finally, we'll look at how scientists are scrambling to find that perfect balance to keep the hero in control.
Okay, so to really get that internal battle we were just talking about, you first got to understand Zirconia's basic personality. And honestly, it's a total shapeshifter, a true ceramic chameleon.
And right away, that leads us to this really weird paradox. How can something be so strong, but at the same time so fragile that it needs help? I mean, we're talking about a material that, if you leave it to its own devices, would literally tear itself apart. So what's the deal? Well, the secret is all in its internal architecture.
To get this, we need to wrap our heads around something called a crystallographic phase. Just think of it like a building's blueprint, but for atoms. It's the super specific repeating pattern of how all the atoms are stacked together. And just like with a building, if you suddenly try to change that blueprint mid-construction, things are going to get real messy real fast.
So pure zirconia actually has 3 different blueprints or phases, and it loves to switch between them based on temperature. At room temp, it's in a kind of weak, unstable form. You heat it up past 1,000 degrees, and it morphs into a super strong phase. Crank the heat way up, and it becomes this incredibly stable cubic phase. Here's the catch. When it cools back down, it tries to change back, and those transformations cause massive volume shifts, big enough to create so much stress that the material literally cracks itself from the inside out.
So how do we stop it from self-destructing? Well, we basically cheat. Scientists add a tiny pinch of a stabilizer, usually something called yttria. This whole process is called doping, and what it does is it locks in those really useful high-temperature forms even after everything cools down. And this is where the main characters of our story finally show up.
Okay, so that doping lets us decide which of zirconia's personalities get to stick around at room temperature. Let's meet the first one, the tetragonal phase. This guy's the material's built-in bodyguard, its undercover superhero.
This tetragonal phase is what gives zirconia its legendary toughness. But the key word here is metastable. What does that mean? It means it's stable enough for everyday life, but it's also kinda spring-loaded. It's just waiting for an excuse to transform. And that readiness, that's its superpower.
And this is just brilliant. Here's how it works. Say a tiny, microscopic crack starts to form. The stress right at the tip of that crack is the trigger. Instantly, the tetragonal grains right there snap into that weaker monoclinic phase. When they transform, they actually expand by about 5%. And that expansion creates this zone of compression that literally squeezes the crack tip shut and stops it in its tracks. The material actively heals itself. It's absolutely incredible.
But the tetragonal guardian isn't the only phase in the neighborhood. We also have the cubic phase, and we can think of this one as the stable giant. It's calm, it's orderly, and it is very, very stable.
Unlike its jumpy tetragonal neighbor, the cubic phase is totally chill. It won't transform under stress, it just hangs out. Now that sounds great, right? But here's the twist. That stability comes at a huge hitting cost, one that can bring the whole material down.
And that brings us to the core conflict of this whole story, the problematic duo. Because when these two phases, the guardian and the giant, have to live right next to each other, things start to get complicated.
So, on one side, you've got the tough, transformable guardian. On the other, the super stable, non-transforming giant. The really critical difference is how they use that stabilizer, the yttria. See, to become a stable giant, a grain of zirconia has to suck up a lot of yttria. And as you're about to find out, it's not shy about stealing it from its neighbors.
And don't just take my word for it. This quote from the groundbreaking research by Chevalier and his team lays it out perfectly. The cubic phase is greedy. It hoards the stabilizer, and that creates a huge problem for everyone around it.
This microscope image right here, this is basically the scene of the crime. These big, dark, smooth areas labeled A and B, those are the cubic giants, and they're surrounded by an entire ocean of smaller tetragonal guardians at C.
The giants got so big and stable because they literally stole the yttria stabilizer from their next-door neighbors.
And this isn't just a theory. We've got the receipts. Look at these numbers. The cubic grains are sitting pretty with an yttria content over 5%, but the poor tetragonal grains right next to them, down at 2.3%. That's way less than the material's average. They've been completely impoverished, left without enough stabilizers to keep themselves stable.
So what happens to these yttria-starved tetragonal grains, the ones right next to those greedy cubic giants? They become the material's weakest link. They become the exact spots where failure and degradation are pretty much guaranteed to start.
And here it is, the devastating result. This picture shows a big cubic grain after an aging test that mimics years of use. You can literally see the zone of destruction, the microcracking all around it. That's the area where those weakened tetragonal neighbors used to be. They failed, and they started a chain reaction of decay.
Okay, so this brings us to the most important question. How do we manage this mess? How do we find the perfect balance? Well, like a lot of things in material science, it all comes down to control.
The big takeaway here is that the more cubic phase you have, the faster the material ages and breaks down, especially in a wet environment like, say, the human body. This is exactly why some of the early zirconia implants failed. The manufacturing process just wasn't controlled enough.
And that control has to be incredibly precise. Research has shown that to get a strong, long-lasting, age-resistant zirconia, the firing temperature has to be kept in a super narrow window. We're talking right around 1400 to 1450 degrees Celsius. That's the sweet spot. And this slide just sums it all up perfectly. If you go even a little too hot when you're making it, you create more of those greedy cubic giants. That means more weak spots, which means more places for failure to start. So at the end of the day, the goal is to make a material that is jam-packed with as many of those superhero tetragonal guardians as possible, with almost no giants in sight.
So is zirconia a hero or a villain? Well, the answer is, it's both. Its story really shows us that even in our most advanced materials, there's this hidden world of conflict and compromise. And it forces us to ask a bigger question. If a perfect material doesn't exist, how do we learn to design for imperfection? And maybe even learn to use a material's flaws to our advantage?